The first problem says this. We've got a car that accelerates from rest to a velocity of 28 meters per second in 20 seconds. A, what is the average acceleration of the car? And what will be its displacement? And draw a velocity versus time graph. So here's how you do these. You do not need to copy all that down, but what you do need to do is write down what's given. Use given, find, and solve. So we got a car from rest. And I want you to draw silly little drawings of the problem. So here's my car, and it's going to start from rest, so V naught equals 0, and then it's going to be going, here's my car a little ways down the road, and now it's going 28 meters per second. And the time it took to do that is 20 seconds later. And notice how I'm setting this up. You know, this time goes with this velocity right here. So, so what are we trying to find? Well, for A, what is the average acceleration of the car? And since we're dealing with problems that are constant acceleration problems, I don't really need to say average acceleration. We're just going to say the acceleration of the car, because there's no difference between average and instantaneous acceleration if your acceleration is constant throughout the whole problem. What is its displacement? That means I'm trying to find delta x. And draw a velocity versus time graph. So I'll just put V versus t graph. Okay? So that's what you need to do rather than copy down the problem. And now we're going to solve it. But setting up a problem like this, in this way, is you're halfway done. Because now you understand what you're given, you understand what you're trying to find. It's stated in terms of the variables that we use. So now we can get to work and solve it fairly easily. So we're trying to find acceleration, but look at what we're trying to find here. I mean, what we're given. We're given initial velocity, final velocity, time, and we want to find acceleration. What are we not given? And we're not trying to find yet anyway. We're not trying to find delta x. So I want the equation. I want to use the equation that doesn't have delta x in it. So you look on your little list and you'll find this equation. The first one on your list. So write it down. And then take that equation and solve it for your unknown. I'm just going to do that in one step. The acceleration is, subtract is v minus v naught, and then we're going to divide that by time. Now, doesn't this make sense? We define acceleration to be delta v over delta t, and that's exactly what I have here. How much time went by? What's our delta t? 20 seconds. And then v, the final velocity, was given to be 28 meters per second minus my initial velocity, which is given to be 0. And so my acceleration is 1.4 meters per second every second. So if I increase my velocity by 1.4 meters per second every second, and I do that for 20 seconds, and I start from rest, I'll be going 28 meters per second at the end. Then I like it when you put a box around your answer. And we should identify this as part A. And we checked it, we did it right, so we can put a star next to it, like that. Yay, done with part A. Let's do part B. delta x. Now you've got some choices to make, because look, we know just about everything. We know the acceleration, the initial velocity, the final velocity, and the time. So all I need now is an equation with delta x in it. And there's 3 of them on your list. But which one's the best one to use? 2. Why? And that is correct. Why would the second one be the best one to use? Because what if you made a mistake calculating the acceleration? Do you want to carry that mistake to the next part of the problem? No. So what I do is I say, well, let's see. Let's try to solve for delta x without using my calculated acceleration. So I look and find the kinematic equation that doesn't have acceleration in it, and it's this one. Delta x equals v plus v naught divided by 2 times time, right? This is the area of the trapezoid equation. And the nice thing about it, it's already solved for what I'm trying to find. So now I just need to plug in my values. 28 meters per second is my final velocity, plus my starting velocity was 0, divided by 2 times 20 seconds. So delta x equals, well, let's see, 20 divided by 2 is 10, times 28 is 280 meters, because the seconds will cancel that, and you get meters. Okay? And now for part C, we're going to draw the velocity versus time graph. And it's pretty easy on this problem because, well, I know how much time goes by, 20 seconds. So 2, 4, 6, 8, 10. You know what? That's kind of silly. I'm going to do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's good enough. I don't need to make it that big. You know I like big graphs, but here it's not necessary. Now, 28 meters per second, so I'm just going to go 5, 10, 15, 20, 25, 30, 10, 15, 20, 25, 30. And this is going to be velocity in meters per second. Now, I know my starting velocity is right here. And I know what my final velocity is at 20 seconds. It's going to be 28 meters per second. And I just need to connect those dots, and there's my velocity versus time graph. I know what the slope is. It's 1.4 meters per second every second. And one thing you can do is look at the area underneath here. It better turn out to be 280. You don't have to do this part. I'm just showing you that if you go the base times the height divided by 2, well, what is 20 times 30? 20 times, it's not 30, it's 28. So if you go 20 times 28, let's see, 20 seconds, it's the 1/2 the base times the height. Come on, Mike. You get 280. So that works. So we're done with problem number 1. Okay, so here's what I really want you to do. Given, find, and solve, people, with the picture. Don't skimp on that, because if you understand what's given and what you're trying to find, and you can draw a sketch of it and visualize what's happening, you really understand what's happening, that makes the problem so much easier to solve. Okay? And then you just apply the kinematic equations we just developed appropriately, and then, of course, draw the velocity versus time graph. So this is right. Put a star next to it, and if you drew this, woohoo! Okay, you're good. that's all.